Now we'll learn of a special type of Turing machine called as the universal Turing machine. I will use UTM for universal Turing machine. We'll understand what UTM is, and corresponding to this universal Turing machine, there is a language called as universal language. We will use LU to represent universal language, right? So you might wonder, why are we learning all of this? So if you recall, if these are your recursive languages, this is a set of all recursively enumerable languages, and outside this are non-recursively enumerable languages. We have already seen that the diagonalization language LD belongs here, right? Which means it's a non-recursively enumerable language. We know a bunch of languages that are recursive. For example, suppose you have a power n, b power n, c power n such that n is greater than equal to 1, right? So this language we know is recursive, right? So we know this language to be recursive. Are there languages here which are recursively enumerable but not recursive? Look at this. Are there languages which are recursively enumerable but not recursive? We have seen a non-recursively enumerable language. Now we'll first understand the universal Turing machine concept. We'll also understand what is universal language, and in the next couple of videos we'll show that LU is a recursively enumerable language but not recursive. So let's call this language as L1. Okay, this L1 is a recursive language, right? Now we have languages across the spectrum. We have seen recursive languages. I'll prove this to you in the next couple of videos. First, let's understand what UTM is and what universal language is. But I'm giving you a big picture overview here. We have learned that LD is a non-recursively enumerable. Let us also show that LU is a recursively enumerable language, and when I prove that LU, the universal language, is recursively enumerable but not recursive, this will also lead us to halting problem. Again, I'll define halting problem much more formally here, and I'll also prove this. Again, we have been talking about halting problem from the very first video in theory of computation, right? So this basically says, given a computer program and some input, would that program halt or not, right? We'll come to this. So over the next 2 to 3 videos, these are the topics that we will cover. But first, let's understand what is a universal Turing machine. So, okay, before we go there, so let's ask this question, right? So you can think of each Turing machine. You can think of each Turing machine as a program, right? Each Turing machine is a program. For example, I can construct a Turing machine for this. What does that do? That gives me, you can think of it, if you think about it from the world of programming, you can think of Turing machine as a program. And if I give a word, if I give an input, if I give, let's say, A, B, B, C, C, this program can tell me whether this word belongs to this language or not, right? That's one way of thinking about a Turing machine. So now universal Turing machine, now the word universal here basically means a universal Turing machine behaves like a general purpose computer. How do we actually use a computer? Okay. It works like a general purpose computer. So what happens in the real world is, to a general purpose computer, you give a program, right? You give a program and you give inputs, and the computer takes the program and the inputs and generates outputs. That's what it does, right? So imagine if there is a Turing machine. Again, this is a rough analogy that I'm giving you. The exact mathematics of the exact details of universal Turing machine we'll learn in a little while. But this is the intuition behind it. You can think of universal Turing machine. So think about it like this, right? A universal Turing machine is also a Turing machine. Remember, a universal Turing machine is a special type of Turing machine that takes, it's a Turing machine that takes a Turing machine code, What is a Turing machine code? A Turing machine code is nothing but the binary strings. We have seen this, right? I can encode a Turing machine using a binary string. A Turing machine code is nothing but the binary string. This Turing machine code, or the binary representation of a Turing machine. It takes a Turing machine code as input, and it takes a word as input, as inputs. It takes 2 inputs, right? So it takes 2 inputs. The first input is the Turing machine code itself. You can think of the Turing machine code as the program, and it takes a word also as input. And what it does now, it takes both. Remember, UTM itself is a Turing machine, but it's a special type of Turing machine. And this Turing machine, so it takes these 2 inputs and it accepts the inputs. It accepts this input. It accepts the inputs. The input word, right? The input word consists of Turing machine code and the word that we want that we want, and a word. Okay, I'll tell you why how this word and Turing machine are related, right? So it's a Turing machine that takes a Turing machine code and a word as inputs, and it accepts the input word. It accepts the inputs or input word if and only if this word W belongs to the language accepted by this Turing machine. So let's call this Turing machine as M, right? So let's call this Turing machine as M, right? So universal Turing machine takes a Turing machine code M as input, and it takes a string W as input. It is taking two things as input, and it accepts the inputs if and only if this word belongs to this Turing machine. So in a nutshell, this universal Turing machine is executing this Turing machine, and it is verifying whether this Turing machine will accept this word or not. That's what it does. In a nutshell, that's what it's doing. Now your question should be, how do we input? See, there are two inputs here, right? There is a Turing machine code and there is a word as an input. How do I input both of them as inputs? Right? So we'll come to, again, this is the big idea. I'll explain you how the whole UTM works internally. Just take, in a few minutes you'll understand this, right? So how do we input? So input to a UTM. How do we input to a universal Turing machine? Very simple. You take the code, the binary code, right? You take the binary code. So I'll use the words binary string and binary code, right? I'll take the code for M, right? This is a binary string. Remember that this is a binary string. This is a binary string. This is the binary representation of your machine M. Then I'll place 3 ones. I'll place 3 ones here, because in the code for M, you will not encounter 3 ones anywhere. You'll encounter a 1 or you'll encounter 2 ones. Look at this. How did we define the whole binary representation of Turing machines? You have ones separating each of the symbols in a single transition. 2 transitions are delimited or separated using 2 ones. You will never encounter 3 ones, right? So what I'll do now is this. So because I want to give the code for M, and now I'll also give the word itself. So this triple one here, this triple one is working as a delimiter or a separator. This is working as a delimiter or a separator between the code for M and the input itself. This is how I input to a Turing machine or to a UTM. To a UTM, I need to send 2 inputs, right? One input is the Turing machine code itself. The second input is the word itself. This is how I input it. If you notice, this belongs to 0 plus 1 star. This is also a binary string, right? As long as your word itself is a binary string. Here I'm assuming by default, from now onwards, I assume that the word is a binary string, unless stated otherwise. Okay. So I'm assuming that the word is a binary string. The code for my Turing machine M itself is a binary string. So this whole thing is a binary string, right? So this is how I give my inputs, right? Very simple. Now I can define so look at this. I can define my language U. Look at this. I can define my language U or the universal language as follows. Now so these are all binary strings, right? So this is a set of strings. Look at this. This is a set of strings. Okay. So let me write it in English. I think that's better. Okay. Okay. So let me write it slightly differently so that it becomes easier for you to grasp this concept, right? So now these are the inputs to a universal Turing machine. On some inputs, on some input words, right? On some input words, right? You don't have 2 inputs now. You have a single input word because I concatenated the 2 inputs using a delimiter. On some inputs, your universal Turing machine will accept them. On some inputs, universal Turing machine accepts. On others, because it's a Turing machine, because it's at the end of the day, UTM is also a TM, right? UTM, for some, it accepts and halts, right? Accepts basically means final state plus halt, right? That's what accept basically means, right? Accept basically means final state plus halt. Or it rejects. There is another possibility. It rejects, which means non-final state plus halt, or it goes into an infinite loop. Right? So all the words, all the inputs on which your UTM accepts. Okay, let's call that language as LU. So LU is nothing but the language accepted by U, where U itself is a universal Turing machine. If I call universal Turing machine as U, LU is the language accepted by U, which means it consists of all the words, all the binary words, such that when I interpret this binary word as a code for a Turing machine delimited by 111 and a word, if this word is accepted by this Turing machine M, then I will accept it even in the UTM, right? Then this whole binary word is accepted by the UTM. That's how I'm defining. And this language is called as a universal language. And this language is called the universal language. Now the big question here is, again, we'll understand the properties of universal language over the next couple of videos. But the big question here is, how does the UTM work? How does the UTM itself work? Because what should the UTM do if you think about it? The UTM takes the code for M. UTM also takes the word. Now it has to simulate exactly how this Turing machine works on this input, and on this input, if this Turing machine goes to a final state and halts, then the UTM should also say, yes, this word is accepted by this Turing machine, else not, right? So that's how it has to work. Now let's try to see how this UTM actually works. I've given you a high level overview, but let's go step by step. Okay. So the working of a UTM, right? The workings of a UTM. So let's call the UTM itself as U. Okay. We'll define the UTM. We'll use the term U or the alphabet U to represent a UTM. Now the UTM has 3 tapes. Okay. So let me go one by one. The first tape, right? Let's call this as tape 1. It has 3 tapes, right? The second tape, T2. The third tape, T3. Okay. Because we know, remember, a UTM is also a Turing machine, and a multi-tape Turing machine is equal to a single tape Turing machine. We've discussed about that equality, right? If I can have a multi-tape Turing machine, I can show that it's equivalent to a single tape Turing machine, right? So the way I will simulate, again, what is my task here? I have to simulate the working of this Turing machine M, whose code we have, on this word W, and see if upon ingesting this word, does this Turing machine reach a final state or not? Does it accept or not? That's all. Basically, that's what we have to determine. So what we'll do is step by step like this, right? So on tape 1, I'll actually give the code. So let's assume M is the code. So let's assume M is the code for your Turing machine. Actually, let me write the whole thing, right? So the code for M, then delimited by the word itself. This is what I have on my tape 1. So my tape 1 consists of 2 parts. My tape 1 consists of the code for Turing machine M, 3 ones as a delimiter, and the word itself, right? That's what my tape 1 consists of. I will use my tape 2. I'll use my tape 2 as the tape of Turing machine M. Look at this. I have a Turing machine here, right? M here, right? This M also has a tape internally. This M, look at this. If you think about it, if I have to simulate this M, I need to simulate the tape of M. So I will use this tape 2 to simulate the tape of the Turing machine M here. So this Turing machine is M. This whole Turing machine is U. T3 itself I'll use to store the current state. I'll use T3 itself to store the current state of this Turing machine M while I am simulating the whole thing during simulation. I'll explain how the whole simulation works. It's actually fairly straightforward. Once you see it, it all becomes straightforward, right? Of course, all of them are infinite tapes. Nothing stops us from having infinite tapes here. It's a multi-tape. So U itself is a 3-tape Turing machine, right? So now let's go and understand how step by step everything works. The first step that I'll do here, the very first step is, first I'll check if M is valid code or not. Look at it, very important, right? For check if M is valid. If M is a valid Turing machine code. If M is a valid Turing machine code. Right? So we can all see, I also have a finite control here, right? I have a finite control unit. Let's not forget it. For this finite control unit, what I'll do here is, I have a string here. Look at this. I have a binary string here. This is nothing but a series of zeros and ones, right? So this code for M, I'll start scanning it and I'll see if it's a valid Turing machine code or not. So valid Turing machine code should not start with 1, and it has to have this exact pattern. Look at this. It has to exactly have this type of strings, right? It exactly needs to have this. If if it has strings which are valid, which is very easy to check, right? You can just have a bunch of transitions and check for that. The moment you check this, suppose if it is not, okay, check if M is valid. If not, no. If it is yes, we'll continue. If it is no, then what do we know? We know that the language accepted by the Turing machine is a null set. We know that. Which means this word will never be accepted by this, which implies W doesn't belong to the language accepted by machine, which implies, then what should I do? Then the universal Turing machine simply halts and rejects. Halt plus reject. Done. Problem solved. First step. First step is a check if M is valid or not. Second step. Okay, let's go to the second step now. Let's assume yes. Okay, yes, continue. Okay, the second option is yes, it's a valid Turing machine, then continue. Right? If it's not a valid Turing machine, then again, to check whether it's a valid Turing machine or not, I can write some simple transitions in my finite control unit of U itself. See, this whole thing is my U. So let me draw the boundary box here, right? So this whole thing is my universal Turing machine U, right? Including this FCU, the finite control unit, right? So now comes the second step. What I'll do now is whatever is W, whatever is the input. Look at this. On T2, we want to simulate the tape of M. Now, when I'm trying to simulate M, imagine M itself is running. Then what happens then? This W will be present on the tape of M. So I will copy W here. So I will copy W from T1 to T2. And that is very simple. The finite control unit can do that. How does it do that? It keeps scanning this till the time it encounters 3 ones. The moment it encounters 3 ones, it will keep scanning everything, whatever it sees, because it has 3 heads, right? Look at this. This finite control unit has 3 tapes, which means it has 3 heads. So whatever it reads here, it will write here till the time it encounters a blank. Look at this. There will be blanks here, right? Obviously, there will be blanks on this tape. So till the time it encounters a blank, it will keep copying it. It will read from this and it will write to this. We can do that, right? Because we have 3 independent read-write heads, right? So copy W from T1 to T2. Second step. Third step, right? Third step. Initialize T3. Initialize T3 with the initial state. Initialize T3 with initial state of M. What is the initial state of M? In the binary encoding, we said Q1 is always the default initial state. Let's go back there. Okay, I'll keep going back there so that, see, what did we say? Q1 is always thought of as the initial state, right? When we did the binary encoding of a Turing machine, right? So let's go back there again now. Okay. So what is the initial state? Q1, which means how do you represent Q1 here? You will have blank, blank. This is 1, blank, blank, blank. Sorry, 0, not 1. Sorry. This 1, 0 basically represents Q1, right? And my read-write head is here. Initially, my read-write head for this will be here. My read-write head will be here. Now I'm starting everything, right? Very simple code. 3 steps. First 3 steps are done. Next comes the whole simulation part. Next, what do I have to do? Look at this. The next step that I have to do, the 4th step is I have to simulate Turing machine M using tapes T1, T2 and T3. Okay, let's see how to do that. It's not rocket science. It's actually simple. So right now, what is my state right now? My current state is Q1 because there is only 1, 0 here. My current state is Q1. Suppose I have an input word also here. Let's assume my input word. Here we assume all the words belong to 0 plus 1 star. Okay, just for simplicity. Let's assume my input word is 0, 0, 1, 1. Let's just say, for example. Okay, I just wanted to explain this with an example. Then what do I want? What transition should I look for? My current state is Q1. My current state is Q1. My input is 0. So what is the transition on this? Right? That's what I need to obtain now. Now, let's assume, because we have 2 symbols here. My W consists of zeros and ones. What are my symbols? X1, X2, X3, if you recall. Right? This is what, if you recall the binary encoding of a Turing machine, you can go back and check that also. So I'll assume that 0 is X1, 1 is X2, blank is X3. Then I can write this as, look at this, then I can write this as X1. On this input, now on this input, what is the output? I need to find this first. Because my input right now, because 0 is nothing but X1. 0 is X1. Okay. Next, my state is Q1. Look at this. My state is Q1 because there is only 1, 0 here. Now I need to find what is the transition for this. For that, there is a code for M. Look at this. There is a code for M. There is a binary code for M. So I'll start scanning. So now what I'll do, I'll start scan the code for M. Scan the code for M. I keep scanning till the time I get this. Look at this. What I want here is a 0 corresponding to Q1, a delimiter, a 0 corresponding to X1. When I encounter this pattern, again, this can either be at the starting or this can be here, which means there is some other transition here. The moment I look for this, the moment I encounter this pattern, I can easily discover this pattern, right? Using my finite control unit. The moment I discover this pattern, the moment I discover this 0, 1, 0, 1, what does this imply? Look at how we designed, how we encoded the transitions of the Turing machine M itself. This basically means the transition on Q1, X1, because there is only 1 here. This is 0 power 1, 0 power 1, right? Then let's assume here that I have 2 zeros after this, 1. Then let's assume I also have 2 zeros, 1, 2 zeros, double 1. So now I'll read this. Now what does this 2 zeros basically mean? This means on Q1, X1, I should transition to Q2. Look at this. It says I should transition to Q2, right? And instead of X1, my tape symbol should be X2. My tape symbol should be X2. What is X2? X2 is nothing but 1. And I should move right. So this implies right, right? This implies right, right? So what I've done here is I've scanned the code for M for this transition. Because look at this. My current symbol I have here. My current state I have here, right? Based on these two, I'll start looking for this code here. I would start looking for the code on my Turing machine M. So the moment I find this, I know where I need to transition. My next state is Q2. The moment my next state is Q2, what I'll do here is, I want to jump from Q, this is Q1, right? Because there is only 1 0. I want to jump to Q2, which means I'll edit this to have 2 zeros. The moment it has 2 zeros, what does this mean? This means my current state is Q2, right? I'm simulating my state here. Look at this. I'm keeping track of my states here. Number 1. Then my input has to be changed to 1 because X2 equals to 1, right? So what I'll do here, I'll change this 0 to 1. Look at this. Because I have these read-write heads, I can change each of them independently, right? Next, I have to move right. So what does this say? I have to move right. So I'll simply move right. My read-write head now will move right. My read-write head now will move right. Right. Next, what do I have? Next, my state is again scan for it. Next, what is my state? Q2 on 1, right? Q2 on what is my input now? My input now is 0. Sorry, my input now is again 0. Q2 on 0. What is 0? 0 is nothing but X1, right? 0 is nothing but X1. Now, how do I find what this transition should be? Now, I should again scan the code here, and I should look for some other transition here. Then Q2. What is Q2? 2 zeros, X1. So this whole thing corresponds to Q2 X1. Then I'll get something else again. So I'll get some other transition, right? So let's assume this transitions to some other state, changes X1 to something right or left, right? So based on that, again, just like the way we have done in the previous step, I'll change the state, I'll replace this, and I'll keep doing it. I can keep doing this. Look at this. I keep doing the same thing till the time I reach a final state or till the time I've exhausted the whole input, right? Now, the way UTM now accepts or rejects is as follows. Look at this. Now I've simulated the whole thing, right? So step 5, I'm simulating the whole Turing machine M using these 3 tapes, right? And we've seen how to simulate it. It's very simple. Now, if M accepts W, which means, what does that mean? It means by reading W, if I reach a final state, I know what the final state here, right? The final state always, by default, the final state is Q2. We already talked about it. By default, in the binary encoding, the final state is Q2, the initial state is Q1, right? So if I've reached a final state and if I've halted, so final state plus halt. So by reading or while reading W, if I reach a final state and if I halt, then M accepts W, right? And I can easily decipher that, right? How do I know that I have halted? If I don't have any other transitions. If, for example, for something like this, if no transition is defined, right, then I know that I am halting there. I can't do anything from there. So I have halted, and if the state that I'm currently in is a final state, then M accepts W, and UTM can easily detect it. Then then the UTM, the universal Turing machine, also accepts, the Turing machine also accepts the input. What is the input here? The code for M. So let me write this down below here. So the UTM also accepts the input. What is the input for the UTM? The input for the UTM is the code for Turing machine M 111W. Look at this. So we know when the Turing, so when M accepts W, which means through this simulation, if I reach a final state and if I've halted while I'm performing the simulation, then the UTM also says, yes, we have reached a final state. And I know we have reached a final state because Q2 is the only final state. And we have halted because there is no transition defined in my whole set of transitions in the code for M. Once I do that, it says, I'm also going to accept it. Simply speaking, that's what it does. That's what it does in a nutshell. Very simple concept here, right? So I hope you have understood how a universal Turing machine works, very importantly, and LU itself, because this is a very, very important language. LU is a set of input strings to the universal Turing machine, which are of this format, right? And LU consists of those strings, which when interpreted as code for M 111W, if the W is accepted by this Turing machine represented by this code, then this whole string is also accepted by my universal Turing machine, right? That's the flow here. Again, the inner workings of a universal Turing machine are very simple. It's a simple simulation task. And remember that universal Turing machine is also a Turing machine, because given this 3-tape Turing machine, I can also always construct a 1-tape Turing machine that is equivalent to it, or a single-tape Turing machine equivalent to it. So a universal Turing machine is also a Turing machine. Let's not forget that. Very importantly, so if you think about it, a universal Turing machine behaves like a general purpose computer, which takes a program and some input, and it determines and it generates whatever output you expect to generate on this input given this program. So in our case, it's languages. Is this word accepted by this program, right? If so, then my UTM or my general purpose computer also will say, yes, this word is accepted by this program. So UTM in a nutshell is simulating a Turing machine on an input using 3 tapes. Now the next important task for us is to prove that the universal language itself is here. It is recursively enumerable, but not recursive. We'll show that with a very interesting idea called reductions. We'll show that in the next couple of videos.